Okay, let's make a start. Thank you very much for joining this SimScale demo and discussion session on rotating machinery. If you've got any questions as we're going through, please feel free to ask your questions in the questions section of GoToWebinar. That should be down the bottom right-hand side of your screen, and we'd be very happy to answer your questions at the end of the session. Okay, so first of all, I'll introduce myself. I'm Steve Laney. I'm an application engineering manager at SimScale, and I will be your host today. Anirudh is going to be the star of the show. He'll be presenting to you today. Anirudh is one of our application engineers, and he has a background in CFD for mechanical design in the automotive and in the aerospace industry. And he has a master's in mechanical engineering from Carnegie Mellon University. And he's a valued part of our application engineering team here at SimScale. First of all, though, I'm going to give you an introduction to SimScale. So who are we? Well, we're a Munich-based company. We were founded in 2012, and we have a global presence. There's millions of simulation jobs being conducted using our software worldwide, and we're funded, so we're going to be here to stay. What do we do? Well, at SimScale, we created the world's first cloud-based engineering simulation platform for fluid dynamics CFD, solid mechanics FEA, and thermodynamic simulations. And we leverage the capabilities of cloud-hosted simulation to give you all of this in just a web browser. There's thousands of brands worldwide that trust SimScale and use SimScale for their simulation jobs. Here on the screen, you can see a select few of those brands that trust us. So what do we deliver them? Well, we enable them to simulate earlier in the design process and accelerate their design process. They can test performance, optimize their products for durability, and improve their design efficiency with cloud-based simulation platform. How does this compare to a traditional CAE solution? Well, with a traditional CAE solution, you typically have high fixed costs. These high costs are associated to the specialist hardware that is required to be installed and maintained on-premise, as well as the specialist software that has to be installed and maintained on that hardware. Traditional CAE tools are also built for specialists, which means that they have to have specialist training and extensive experience to get the most out of the software. And computing time is typically measured in days or weeks, and it can be very difficult to parallelize computations because during a simulation, the hardware and software is occupied. So, how does this compare to what we offer at SimScale? Well, with SimScale, there's no upfront investment. There's no installation or maintenance of expensive hardware or software. It's very easy to get started and set up. All you need to do is visit our website, log in and create an account, and you're ready to go. We enable seamless collaboration within your organization, and we provide world-class support. From within the software, you can access a chat panel so that you can talk to one of our experts during your simulation. Typically, the computation time is measured in minutes rather than weeks. And because we're leveraging the capabilities of cloud-hosted simulation, you can run as many simulations in parallel as you like. Okay, so that's the introduction from me. And now I'm going to hand you over to Anirudh for the demonstration. Please do remember to ask any questions you've got as we go. Thanks, Anirudh.
And thank you for that introduction, Steve. Yeah, so I'm really excited to take you through SimScale today and showcase some of the features and see how you can apply it to study any kind of rotating machinery. So the example I have for you today is of a Francis water turbine, as you can see here on the screen. but all the principles, all the setup procedure that I show you is valid for any kind of rotating machinery, really. So this includes things like pumps, industrial fans, blowers, compressors, propellers. Anything with a rotational component on it can be simulated on the platform. The reason I chose Francis turbines specifically is that they're a good example because they combine axial and radial flow, and they're used very heavily in the hydropower industry, accounting for more than 60% of the global hydropower output. So any improvements that we can make in the efficiency can have a significant impact. So the objective today is to look at the design of a Francis water turbine, see how we can optimize it, and also characterize its performance. So I'm going to take you through a couple of slides quickly to show you the setup of the geometry that we're working with, and then we'll dive into the platform, look at some results, and I'll show you how to set up the simulation. And then we'll come back to some slides and take a look at some additional results. So just to set up the problem that we have, this is the CAD that I'm using. As you can see, I have a pretty straightforward Francis turbine with an inlet here. The water flows in from here, moves around through the spiral casing, where it hits this first set of fixed blades, and those direct the flow towards these moving blades in the center. So these are known as the runners, and they're the ones that generate all the power. So you can think of the runners as rotating blades or the rotor, and the fixed blades as the stator. So once the water moves through the blades, it goes down this draft tube and exits out of the back. And this is there to equalize the pressure and minimize any losses in that exit process. So a quick brief on the simulation setup. What I'm doing here is I'm specifying a couple of things. So the case I'm studying, I want to specify the performance at a certain flow rate at the inlet. At the outlet, I'm just specifying a zero static pressure. And I'm also specifying a rotation for my blades. So this is the case I'm simulating, and I'm going to show you the results for. It is fully incompressible, steady state flow and fully turbulent. So let's look at the results for some of this for a simulation like this. Let's jump into the platform and look at the results. So if you haven't seen it before, this is the SimScale workbench. This is the user experience. So the first thing I want to point out is right up top, you can see the URL. So SimScale is completely cloud-based. There's no installation or any sort of specialized hardware required to run this. I'm just using a simple Lenovo ThinkPad as my work laptop. And with a decent internet connection, I can simulate most problems that I need to. So up top, we have a couple of collaboration features. So you can share your project with other people in your team. You can even share edit access or copy access. So this is like you can think of it as a Google Docs sort of approach to collaboration where multiple people can work on the same simulation. You can also copy projects. So if you have a colleague who's done a simulation, it's very easy to just copy that and start simulating on your own. On the left is the Geometries tab, where you upload your different designs. At the bottom, we have the simulation. So this is where you interact with setup of the simulation. And as you can see, it's pretty clean. It's pretty straightforward. There's no messy toolbars that I have to worry about. I have a big 3D viewer in the center, which is occupying most of the real estate. Right, so now we're looking at the results for the simulation that I have showed you the setup for. So let's look at the kind of design inputs or the kind of results that you can get out of running a simulation like this to inform some of your design decisions. So right now what we're looking at is velocity streamlines. So these are known as particle traces on the platform. So as the name suggests, we're tracing a particle as it moves through the domain from the inlet through to the blades, and it goes out the outlet. So this is a great tool for understanding some of the larger flow features in my domain and get a good qualitative understanding of the flow. So I can visualize how the flow is coming out of my turbine blades, and I can see the swirl or the rotational component that is imparted on them and how it gets out of the draft tube. So now I'm interested in characterizing the performance of this turbine. So I want to know the flow rate and the pressure head across it, since those are the key terms for a turbine. So let me pause this animation and turn off this particle trace. So what I can do is, instead of coloring this part, say a gray color, I can color it by the pressure and look at the pressure head. So once I have it colored by pressure, I can select the inlet and I can use this bulk calculator on the top right, which will give me some statistics for this phase. So it'll tell me the average pressure, and I can use this to calculate the pressure delta across my system. So if I'm not happy with pascals, I can very easily just change the unit to say PSI, and that way I can get the pressure drop across my system very easily. So now that I know the pressure drop across my system, I want to know the flow rate that this is pulling through the system. So instead of looking at the pressure, I can very easily change this to velocity. So when I do that, you will notice that instead of the average pressure, I see the average velocity. And at the bottom, I also get the volumetric flow rate. So this is very useful to get some of the bulk features in your domain. So now that I have a good understanding of the overall performance of my turbine, I want to dig in a little bit deeper and understand what is going on at the blade level. So in order to do that, I have a few tools at my disposal. So I have something known as a cutting plane, which, as the name suggests, slices the domain through the middle, and we can visualize what's happening at the inside. So now I'm looking at the velocity around my blades, and straight away I can see using these vector arrows the direction of the flow, and I can make out that around my stator blades, I'm seeing a lot of flow separation here. So around the blades on the left, the flow is slightly more attached, but most of the blades on the right of my screen, I can see a significant amount of flow separation as well as recirculation that moves throughout. So this is something that I can definitely improve on my design. So now that I've kind of understood how the flow is around my blades, I want to know how my draft tube is performing. So what I can do is, instead of looking at a plane across my blades, let me just turn off the vectors, and I can very easily just change the normal. So I can look at my view cube and see that in order to view the draft tube, I want it going through my X normal. So let me just change the normal to X and change the result quantity I am looking at. So for the draft tube, I'm more interested in the pressure. So I can turn off these vectors and change the result quantity back to pressure. And that way I can visualize the pressure differential across my draft tube. So ideally with the draft tube, you want the pressure differential to be as smooth as possible so that you can minimize any losses. So straight away I can see that based on the color legend, the transition from green to yellow isn't as smooth. Again, this is something that I can improve because I see a slightly steeper gradient here than I would want to. I can investigate this further by using my inspect point tool and click on any face or any point and get the pressure value. So this way I can click on a couple of points and I can see that the transition is, or the pressure gradient is pretty high. So this is not ideal, and this is something that we can improve, as I will show you later. Right, so this is just a quick overview of the type of results that you can get from running a simulation like this. Now I'm going to show you how I set this up. So let's start with the geometry. So with SimScale, you can upload any number of designs using the plus button here. You can upload multiple different formats. So we work with all typical CAD formats as mentioned here, and of course more that you can find out by clicking here. So I've got a couple of designs here, and on the right, I can see the breakdown of my CAD. So what I have is the fluid domain, as well as another second CAD body, which is just a cylinder around my blades so that I can model my rotation. So now that I have my CAD in place, I can start simulating. I'll hit create simulation, and this opens up all the types of analyses that SimScale offers. So as you can see, it's not just fluid dynamics. You can simulate heat transfer as well. And say you're interested in the structural side and you want to know the forces on your blade or on your casing or how the structural side reacts, you can do that by running our FEA simulations down at the bottom. So in my case, because I'm just interested in the flow, I'm going to choose incompressible and hit create simulation. So you'll notice when I do that, I get a new simulation called incompressible 3 under my simulation tree. So I can just rename this to whatever I want. I can call this Thursday demo or design 1 or design 3 or whatever I need. So the workflow is pretty straightforward. It's top to bottom. So you can see here that I have a few nodes in my tree and I have a couple of red circles. So I need to get green checkboxes everywhere, and that'll allow me to run a simulation. So going from top to bottom, I can see that there's a couple of things I need to change here. So I need to add the material properties as well as the boundary conditions. So let's start with the material properties. When I click that, it opens up our material library. There's a bunch of materials. I'm just going to choose water here. The important thing to note is that you can change any of these properties. So all these fields are editable. So if you had a fluid or a mixture, say water at a different temperature, I can edit the density and even rename the fluid to say a custom material that I have. The next thing is boundary conditions. So this is where I'm specifying my inlets and outlets. So if you recall, I'd mentioned that I want to specify a flow rate for this system, and I can do that by selecting velocity inlet. So here it's telling me that I think I didn't click the plus button after editing, so I can hit the checkbox. So if you don't assign, if you still have a red circle, it'll give you an error and it won't let you move forward. So I think I didn't assign it to the right geometry. So now that I have done that, I have the green circle under my materials and I can move on to my boundary conditions. So let's start with the velocity. So instead of specifying the velocity in components like the X, Y, Z here, I want to specify the flow rate, and I can very easily do that by selecting volumetric flow and specifying, say, 16 meter cubed through my system. At the outlet, it's pretty straightforward. It's just zero pressure, so I can choose pressure outlet and select my outlet phase. So now that I've specified the inlets and outlets, the only thing I need to do is specify my rotation, and that is hidden under advanced concepts here. So we have something called rotating zones, and in this case, we will use an MRF rotating zone. So an MRF stands for multiple reference frames. So what this means is that we have two reference frames. So one is just the fluid region, and the second is the cylindrical body that I was talking about. So I can just select that, and what I need to do after that is just specify the origin of that reference frame as well as the axis of rotation. So in my case, it's going to be -1 here in the y direction, and then I can specify the rotation. So 350 RPM is going to be about 36.6 radians per second. And now that I've specified, I'm good to go. So since I have these two reference frames, I can run a steady state simulation and intelligently combine the data from both instead of having to use, say, a moving mesh or a transient approach. Right, so now that my setup is done, I have green checkboxes everywhere and I'm good to go. I can start a new simulation run by clicking the plus button here. And the software will tell me some estimates for how much time the simulation is going to take and how many computational resources it's going to use. So I can just hit start, and you'll notice when I do that, the job is sent off to the cloud. So this is what running in the background on a virtual machine in the cloud. And when the simulation is complete, I'll get an email and I can come back and post-process. So while the simulation is running in the background, we are not limited to waiting for it. So while this is running, I can do further pre-processing or post-processing. I can even set off a different simulation. So if I want to characterize the performance of this blade at different flow rates, what I can do is very easily just change the flow rate here, hit OK, and start a new simulation with run 2. So I'll just call this 12 meter cube per second, and that way I can characterize my performance at different flow rates. So when I do that, this run is sent off to a different machine in the cloud, and this is how you can harness SimScale's parallel computing capabilities. You're not limited in the number of machines, so you can theoretically use an infinite number of machines to run n number of designs. So now that I've set off a couple of runs to study the performance of this design, I want to look at a second design as well. So as we had noticed with this design, we had a couple of problems with it. There was significant flow separation at the stators, and the draft tube pressure differential was a bit higher. So I have a second design here with slightly different stator angles, and it also has a different draft tube design. As you can see, it's got a square opening at the back as well. So if I want to study this design, I don't need to set up another simulation from scratch. What I can do is just duplicate my existing simulation. So when I hit that, I get a copy of that simulation, and all the inputs, all the changes that I had made are preserved. All I need to do is switch out the geometry and reassign these things, and I'm good to go. So this is just a quick overview of how you can set up any of these analyses. If you have any questions about the setup side, please feel free to use the questions functionality right now and ask those. So now that I've shown you how you can set up a couple of different simulations, let's go back to the presentation and compare some results for both. So on the left, we have the first design that I had shown you, and on the right is the second modified design with a slightly different stator blades, as well as a different draft tube at the back. So right now what I'm doing is visualizing a cut plane to get the velocity around the stator blades. So if you recall, we had noticed a lot of flow separation around these blades, and you can see that in this image. With the second design, I have changed the angle of attack of these blades, and you can see immediately that the flow separation is a lot lesser. So therefore, some of the energy waste from the water is going to be minimized, and this is one way to improve the design. Next, let's take a look at the draft tube. So with our first design, immediately the first thing we spotted was that the pressure gradient in this section of the neck wasn't as smooth. As you can see, the transition from green to yellow, according to this legend, is not as straight. With the second design, where I have the square draft tube and a slightly longer neck for this, I can immediately see that that transition is a lot smoother. So this will help me minimize any losses through this exit tube. Right. So let's look at the tip or the exit of the draft tube here and compare the two designs. So I'm looking at velocity streamlines, and I want to compare what's happening between my circular draft tube and the second and improved square one. So here, as you can see with the circular draft tube, the swirl or the rotational component of these of the flow here is a lot higher. So that means more energy is being wasted in the form of rotation, and we want to minimize that. And we are doing that to a certain extent with this square draft tube. Here you can see that the rotation is a lot less. The next thing I want to look at is the performance of the turbine in terms of its blade efficiency. So here I'm plotting the pressure on the blade surfaces at the front and the back, and this is then used to calculate the power that the blades generate. So this can then be used to get your efficiency, and that is critical if you want to improve the design. The last thing I want to show you are a couple of performance curves that you can generate. So if you recall, I set up a couple of simulations at different flow rate. So that is what I have here. At the bottom, I have different flow rates, and in the y-axis, I'm plotting efficiency. So I'm comparing these two designs at different operating points, and I can see that with my modified design, with the slightly better stator angles and the improved draft tube, I am seeing a significant jump in efficiency. On the right, I'm looking at a graph of the stator angle versus the efficiency. So I showed you a couple of designs with different stator blade angles. Here I have a few more angles, and I want to see how the efficiency changes with that. So I can use this plot to identify which is the best efficiency point or the best operating point for my design. Right. So I know that I've covered a lot of information in the last 15 minutes. So if you have any questions about this, please feel free to ask them right now.
Great, thanks for that, Anirudh. That was a great presentation. Yeah, please feel free to ask any more questions that you've got. We've had a few come in, so we'll do our best to answer all of those now. Anirudh, the first question is whether we provide training for using SimScale.
Sure, that's a very good question. So yeah, with a professional license, we do include training. You also have the option to get training for newer employees if they join later. And you also have the option to do a guided onboarding project. So this is like a first project where we will basically hold your hand, walk you through the setup for your geometry, tell you the best practices, and you can use that as a template. Now, in general, if you want to learn SimScale, we do have a lot of tutorials and public projects. So the example I showed you for this Francis turbine, it is a common tutorial that you can find up on our website if you just Google SimScale tutorials, and you'll find a bunch of simulations there. So you can use those really to follow along and learn more about the software.
Great, thanks, Anirudh. That's really similar to another question we had actually. Someone else has said, can you please send the link of the webinar recording after this session so that we can follow and try? Of course, yes, everyone who's signed up is going to receive the recording. And as Anirudh said, this same project is available to use as a template and follow along. Is there anything you'd add to that, Anirudh?
Yeah, I'd say it's the best thing about our tutorials is once you find them on our website, you will be able to find the initial tutorial with just the geometry on it. So we'll tell you how to set it up. But in case you do mess something up, we also have a second version of the tutorials, which has the results in it already. So you can follow along. In case you mess something up, you can just look at the final version, and that'll allow you to post-process and look at some of the results that you can get from that tutorial. So I'd say it's a pretty intuitive and straightforward process, and it's pretty easy to sign up. So all you need is an email ID. You can create a SimScale account and get started pretty quickly.
Great. So another question we've had come in is there a way to validate the solver with real-world results?
Yep. So I think that's a good question. I think people for running simulations like this, it is important to have accuracy and have it match real-world data. So the first thing to say on that point is our solver. So we use OpenFOAM, which is a highly validated solver, and it is an industry standard. So it is used heavily in the rotating machinery industry as well, and a lot of other softwares as well use the solver. So on the back end, the equations that we're solving, they are highly proven and validated. Of course, with SimScale, just using our platform itself, we do have a few validation cases up on our website. So if you go to simscale.com/validation, you'll be able to find a lot of cases where we've taken experimental data, whether it's from a test bench or like a wind tunnel, and validated it against our software. So this could be from research papers that we find, and we've proven the accuracy of our solver that way.
Yeah, the great thing about those validation cases is you can open up the project in the platform, run it yourself, and also make changes to it. It's really useful. Okay, so I think we've got time to answer one more of the questions. I apologize if we haven't had time to answer your question. But the last one we'll answer now is, how do you ensure data security if everything is online?
Sure, that's a good question. So with SimScale, by default, all your data is completely private. So nor we nor the cloud servers have access to it. If you do want to give us access to it, it is pretty simple. So you can do that using our support functionality. So we have in-product chat as our main form of support. So if you get stuck anywhere, you can send us a message and a support engineer will get back to you pretty quickly. At the bottom, you have this option to share your project with support. And this gives us view-only access to your project. So that really makes the support instantaneous. So unless you explicitly give us access, all your information is encrypted. Also, it is backed up multiple times. So there's no danger of you losing your information or someone else getting access to it.
Great, thank you. So thank you to everyone for attending, and thank you to Anirudh for that demonstration and for answering the questions. See you next time.
Thank you.